In the silent reaches of the cosmos, where light from ancient suns drifts like whispers across eternity, there are objects so strange that they defy the imagination. They are the remnants of once mighty stars, collapsed in death, yet burning with a kind of eternal endurance. Neutron stars, the densest beacons in the universe, forged in fire, born from destruction. Here, matter itself is crushed beyond its natural form. Atoms, the familiar building blocks of existence, are torn apart under the unbearable weight of gravity. Electrons are driven into protons, leaving behind seas of neutrons, tightly bound in a state that no laboratory on Earth could ever reproduce. What remains is a star no larger than a city, yet holding more mass than the sun. A single teaspoon of its matter would outweigh mountains. In these stellar corpses lies a paradox: annihilation and survival, collapse and endurance entwined. They embody the razor's edge of physics, balancing just shy of the abyss of a black hole, yet refusing to vanish into eternal darkness. How can something so small hold the weight of entire suns? How can matter endure pressures so immense that the very structure of reality seems to fracture? Neutron stars stand as cosmic riddles, both terrifying and mesmerizing, at once a graveyard and a laboratory. A reminder of how little we truly know about the forces that govern existence. They are not merely astronomical curiosities. They are boundaries. They are questions. They are the edge of what the universe allows, and perhaps the first glimpse of what lies beyond. The story of neutron stars begins not with certainty, but with suspicion. In the early decades of the 20th century, humanity had only just begun to glimpse the true scale of the cosmos. Einstein's general theory of relativity had redefined gravity as the curvature of space-time itself. Quantum mechanics had revealed the bizarre, probabilistic world hidden inside the atom. Yet even as these revolutions unfolded, one question loomed over astrophysics: what happens when a star dies? For centuries, stars had seemed like eternal fires, immortal pinpricks of light scattered across the night sky. But new physics brought a new realization. Stars are not infinite. They live, they age, and they must one day collapse. The greater the mass of a star, the more violent its death. In the 1930s, two astronomers, Walter Baade and Fritz Zwicky, working at Caltech, dared to imagine something extraordinary. Studying the violent explosions of supernova, they proposed that the dying core of a massive star could collapse into an object made entirely of neutrons. They called it, simply, a neutron star. It was a radical suggestion. Neutrons themselves had only just been discovered by James Chadwick in 1932. To imagine entire stars reduced to seas of neutrons seemed less like science and more like alchemy. Yet Baade and Zwicky were insistent. They argued that only such a dense remnant could explain the vast energy released in a supernova, an energy so great that for a brief moment a single dying star could outshine an entire galaxy. Still, the idea was met with silence and skepticism. The scientific community, though intrigued, hesitated to believe. A star crushed to the density of an atomic nucleus, a mass of millions of Earths reduced to the size of a city. The very concept sounded absurd. There were no instruments capable of confirming such a thing. Neutron stars, if they existed, were hidden beyond the reach of the telescopes of the time. For decades, the theory lingered like a ghost, bold, provocative, but unproven. The silence lasted until the 1960s. It was an age of space race ambition, of radio telescopes sweeping the skies for signals, of humanity pressing against the edges of the possible. In 1967, a young graduate student at Cambridge University named Jocelyn Bell Burnell was poring over rolls of chart paper from a new radio telescope. The instrument was designed to measure the scintillation of quasars' distant galaxies with blazing cores. But amidst the jagged ink marks of cosmic noise, she noticed something strange. It was a series of pulses, perfectly regular, repeating every 1.337 seconds. The signal was unlike anything seen before, too precise to be random. Noise, too rapid to be a star, too consistent to be man-made interference. At first, it seemed almost playful, as though the universe itself were tapping out a rhythm. Bell and her advisor, Anthony Hewish, jokingly labeled it LGM-1, Little Green Men. The idea that it might be an alien beacon was not entirely dismissed, so strange was the signal. But soon, more pulsating sources were found, each with its own rhythm. The possibility of extraterrestrial intelligence gave way to something even more profound: the discovery of pulsars. Pulsars were revealed to be rotating neutron stars. Their powerful magnetic fields funneled radiation into beams, sweeping across space like the light of a cosmic lighthouse. Each pulse was the heartbeat of a star that had died, collapsed, and been reborn in an unimaginable form. Here, at last, was proof of Bode and Zwicky's forgotten theory. Neutron stars were not just an intellectual speculation. They were real, spinning silently across the galaxy, their signals reaching Earth with clockwork precision. The confirmation was both exhilarating and unsettling. Neutron stars were no longer hidden. They were everywhere, scattered across the Milky Way, objects smaller than London, yet heavier than the sun, flickering with rhythms more precise than any clock humanity had built. They seemed to defy the natural order, to mock the limits of comprehension. The discovery sparked a new branch of astrophysics. Radio astronomers mapped pulsars across the heavens. Some spun once every few seconds, others hundreds of times per second, faster than the blades of a helicopter. Their surfaces reached temperatures of 1,000,000 degrees. Their magnetic fields were 1,000,000,000,000 times stronger than Earth's, and yet, despite this terrifying power, they were beautiful in their precision. Pulsars became the metronomes of the universe, guiding spacecraft, testing Einstein's relativity, and even serving as potential cosmic lighthouses for interstellar navigation. For Jocelyn Bell Burnell, the discovery was personal. She had found a cosmic heartbeat, one that no one had expected to hear. In the decades that followed, she would speak often of the moment she first saw those pulses etched into paper, the moment when theory became reality, and the paradox of neutron stars emerged from silence into science. But the story was not one of triumph alone. The Nobel Prize for the discovery was awarded to Anthony Hewish and Martin Ryle, while Bell Burnell was overlooked, a reflection of the biases of the time. Yet history has restored her place. Her discovery remains one of the most significant in 20th century astronomy, a moment when the universe revealed a secret that had lingered in shadows for 30 years. The paradox was complete. Neutron stars, born in fire, compressed beyond reason, existing on the thin edge between collapse and disappearance, were real. What Bode and Zwicky had once imagined in the 1930s had materialized. The cosmos had whispered its truth, and at last humanity had heard. From that moment, the universe was never the same. No longer was stellar death the end of the story. In the remnants of collapse, a new kind of star had emerged, stranger than fiction, denser than anything known, and destined to challenge every law of physics. Humanity believed it, understood. Neutron stars had been discovered, but their true nature, the unimaginable density of their cores, the paradox of their survival, the secrets they might hold about the fundamental fabric of matter, had only just begun to unfold in the universe. There are boundaries that seem inviolable. The atom, for example, was once believed to be indivisible, the ultimate building block of matter. Its nucleus, a dense knot of protons and neutrons, was thought to be the final frontier of compression. Beyond this, physics offered no path forward. The forces binding the nucleus together, the strong nuclear force, were considered unbreakable, a barrier protecting matter from infinite collapse. And yet, in the heart of dying stars, nature erases those boundaries. Gravity, that most patient and relentless of forces, bends every rule. It crushes atoms until the familiar scaffolding of matter is obliterated. Electrons are driven into protons, annihilating their individuality and giving rise to neutrons. What emerges is a substance so alien that it resists description, nuclear matter in its purest, most extreme form. A neutron star is the consequence of this violence. Imagine a body only about 20 kilometers across, scarcely the size of a city, yet holding more mass than the sun. The density is beyond comprehension. A single teaspoon of neutron star material would weigh as much as a mountain range, billions of tons compressed into a spoon. This is not a poetic exaggeration. It is the cold arithmetic of physics. Matter packed to densities of y kilograms per cubic meter, rivaling the very nuclei of atoms. To scientists of the mid-20th century, this seemed like heresy. How could matter hold together under such crushing conditions? Why did it not collapse into a black hole, vanishing entirely into spacetime's abyss? The existence of neutron stars seemed to contradict the stability of matter itself. The paradox rests on a fragile balance. When stars die, they undergo gravitational collapse. If the star is small, its ashes become a white dwarf, supported by the pressure of electrons resisting further compression. But for larger stars, even electrons are overwhelmed. Gravity forces them into protons, creating neutrons, and the star becomes a neutron star. Yet there is a threshold. If the mass of the collapsing core exceeds about 3 times that of our Sun, not even neutrons can resist. The star collapses beyond the point of no return, becoming a black hole. The mystery is why some stars halt on the razor's edge of neutron degeneracy, while others plunge into complete oblivion. The universe offers no simple answer. At first glance, neutron stars should not exist. The forces involved are incomprehensible. Neutrons themselves are unstable outside of an atomic nucleus, decaying into protons and electrons within minutes. But inside a neutron star, under the crushing embrace of gravity, they are forced into stability. They exist only because the universe compels them to, trapped in conditions no earthly laboratory could reproduce. It is here that the assumptions of physics fracture. Classical mechanics, which once described the motions of stars and planets, offers no refuge. Even quantum mechanics, the theory that explains the strange behavior of particles, begins to falter. The neutron star occupies a liminal space where general relativity, Einstein's vision of gravity, collides with nuclear physics. The laws that govern the very large and the very small are forced into an uneasy truce, and neither fully wins. The surface of a neutron star defies imagination. Gravity there is 200 billion times stronger than on Earth to stand upon it. If one could, would mean being flattened instantly into a film thinner than paper. Light itself bends under the weight of this gravity, curving back toward the star, making the horizon shimmer with distorted echoes of its own form. A photon leaving the surface does so at great cost, its wavelength stretched and reddened by the effort of escape. And yet, this is not a black hole. The light, the star, though impossibly dense, still resists. Somehow, nature has discovered a way to halt collapse before the point of no return. The neutrons themselves, bound by the Pauli exclusion principle, the quantum law that forbids identical particles from occupying the same state, push back against gravity's endless hunger. This is neutron degeneracy, pressure, the final defense of matter, but it is a defense that should, by every intuitive measure, fail. How can quantum laws, invisible on the scale of human life, resist the crushing weight of entire suns? Why should the smallest dictate the fate of the largest? In neutron stars, this paradox is written across the sky. They are a bridge between the atomic and the cosmic, between microphysics and macrocosm, and they should not exist, and yet they do. The shock of this realization reverberated through science. Neutron stars undermined the idea that matter had a natural scale of stability. They revealed that nature is willing to go further, to compress deeper, to rewrite the fabric of matter in pursuit of equilibrium. The stability of ordinary atoms suddenly seemed fragile, contingent, dependent on conditions that could vanish in a heartbeat of cosmic time. Even stranger was the question of what lies beneath the surface. Theories diverged. Some physicists suggested that the interior of a neutron star might be a sea of neutrons, swirling in quantum superfluidity, where friction ceases to exist and particles move as a single coordinated entity. Others proposed that the extreme density could break neutrons apart, releasing their constituent quarks into a soup of subatomic chaos. Such a quark star, if it exists, would be even denser, even stranger than the neutron stars we know. The edge between neutron star and black hole is perhaps the most haunting frontier of all. In one scenario, a collapsing star halts at neutron degeneracy, surviving as a pulsar or magnetar. In another, just a fraction more mass tips the balance, and the star is lost forever into a singularity. The line between endurance and annihilation is vanishingly thin, and it is written in the lives and deaths of stars scattered across the galaxy. Why does nature allow this? Why is there a window where matter halts just before the abyss? Some scientists see it as coincidence, a byproduct of quantum laws written into the universe at its birth. Others view it as a clue, Perhaps neutron stars are laboratories where the secrets of unification between relativity and quantum mechanics are written. To study them is to approach the seams of reality itself. The shock of neutron stars is not only scientific, it is philosophical. They force us to consider the fragility of what we call matter. The chair beneath us, the ground beneath our feet, the earth itself, all of it could be crushed into unimaginable density if placed under sufficient gravity. Stability, it turns out, is not a guarantee but a privilege of circumstance. Neutron stars remind us that the universe is not bound by our assumptions of permanence. The same laws that build the delicate lattice of matter can, under different conditions, destroy it. What we see as solid, immovable, eternal, is, in truth, conditional, fragile, contingent upon balance. That is why neutron stars should not exist. By all ordinary measures, they break the rules. They straddle a frontier where matter loses its identity, where physics teeters on collapse, where every calculation seems to approach the edge of infinity. And yet, scattered across the galaxy, these impossible objects endure, flashing their signals into the dark, daring us to look deeper, to ask harder questions, to acknowledge the strangeness that underpins existence itself. In their paradox, there is both terror and beauty. Terror in the realization that the familiar world could dissolve under the weight of gravity's relentless hand. Beauty in the fact that the universe allows such delicate balancing acts to persist at all. Neutron stars are not just remnants of stellar death. They are proof that reality itself is more flexible, more mysterious, and more improbable than we ever imagined. Neutron stars are among the most elusive objects in the universe. Born in the crucible of supernova, they exist at the intersection of extremes: gravity, density, and magnetic fury. Yet, for decades after their theoretical birth, they remained phantoms, concealed in the cosmic night. To study them, humanity needed instruments capable not of seeing the stars as points of light, but of listening to the universe in wavelengths invisible to the eye. It began with radio telescopes. The discovery of pulsars in 1967 had revealed that neutron stars could announce their presence through beams of radio waves sweeping across space with clockwork precision. These signals became the first window into their hidden interiors. As the technology of radio astronomy advanced, vast arrays of dishes, from Arecibo's Great Bowl in Puerto Rico to the Parkes Observatory in Australia, began mapping the sky, listening for the steady drumming of stellar remnants. Each detection was like finding a cosmic heartbeat. Pulsars rotated with astonishing regularity, some so precise they rivaled the accuracy of atomic clocks. By measuring their pulses, scientists could probe the physics of space itself. The ticking of a pulsar could reveal the presence of a hidden companion star, distortions caused by gravitational waves, or the faint slowing of rotation as the star radiated away its energy. But radio waves were only the beginning. Neutron stars are multi-wavelength creatures, their strange energies spilling across the electromagnetic spectrum. In the 1970s, X-ray observatories placed above Earth's atmosphere revealed another layer of their violence. These stars, though no larger than a city, could blaze with X-rays 100,000 times more powerful than anything the sun emits. NASA's Chandra X-ray Observatory, launched in 1999, and ESAS XMM Newton uncovered searing images of neutron stars glowing with the heat of their crushed interiors. Later, the nicer instrument aboard the International Space Station added detail, measuring their size and structure with exquisite precision. And then, a new frontier emerged. In 2015, the Laser Interferometer Gravitational Wave Observatory (LIGO) made its first detection of ripples in spacetime, confirming Einstein's century-old prediction. 2 years later, the merger of neutron stars, an event labeled GW170817, shook the universe in gravitational waves and light simultaneously. For the first time, humanity observed the collision of these dead stars in multiple messengers: radio, X-ray, gamma-ray, optical, and gravitational. It was the birth of multi-messenger astronomy, a way of seeing the cosmos not through one sense but through many, and it changed astrophysics forever. Through these instruments, neutron stars ceased to be ghosts. They became laboratories, each one a natural experiment in physics beyond human reach. The most extraordinary gift of neutron stars lies in their timing. Pulsars rotate with a steadiness that rivals perfection. The Crab pulsar, born from a supernova witnessed in 1054 by Chinese astronomers, spins about 30 times per second. Millisecond pulsars rotate even faster, more than 700 times per second, faster than the blades of a household blender. These astonishing rotations allow neutron stars to serve as cosmic clocks. Their precision enables astronomers to test the very fabric of reality. The pulses of a neutron star in a binary system orbiting another neutron star can reveal the distortions of spacetime predicted by Einstein's relativity. In 1974, Russell, Hulse, and Joseph Taylor discovered just such a binary pulsar. Over decades of observation, its orbital decay matched exactly the predictions of gravitational radiation, earning them the Nobel Prize in Physics. But these clocks are not immutable. Occasionally, neutron stars glitch. Their rotation suddenly speeds up, as though the star itself had skipped a beat. These glitches are windows into their hidden interiors. They suggest that beneath the crust of a neutron star, the neutrons form a superfluid, a bizarre quantum state with no viscosity, flowing freely through the star's rigid outer layers. When this superfluid suddenly shifts, the star's rotation changes, and Earth-based telescopes record the jolt. Each glitch is a seismic whisper from inside a city-sized sphere heavier than the sun. If pulsars are the steady beacons of neutron stars, magnetars are their demons. These are neutron stars with magnetic fields 1,000 times stronger than ordinary pulsars, trillions of times stronger than Earth's. Their fields are so extreme that they can distort the quantum vacuum itself, turning empty space into a medium that bends light. Magnetars reveal themselves through bursts of high-energy radiation, some so powerful they can be detected across the galaxy. In 2004, a magnetar known as SGR 1806-20 unleashed a flare brighter than the moon. Despite lying 50,000 light-years away, the energy released in a fraction of a second exceeded what the sun emits in 150,000 years. The existence of magnetars forces science to confront the limits of magnetic fields. How can such strength exist without tearing the star apart? What exotic states of matter are conjured in these impossible conditions? The answers remain uncertain, but magnetars remind us that neutron stars are not quiet relics. They are active, volatile, and dangerous. As observations multiplied, patterns emerged. Pulsars slowed predictably over time, their energy bleeding into space. Yet some showed sudden outbursts, giant pulses of radio emission, or irregular flickering as if their lighthouses wavered. Others emitted X-ray bursts without warning, or shifted in brightness over years. These behaviors suggest that neutron stars are not static, but dynamic. Their crusts crack under the strain of rotation, releasing energy in bursts. Their magnetic fields twist and realign, unleashing storms of radiation. Some theories suggest they may even quake seismic vibrations, resonating through a body of pure neutron matter. The deeper the observations, the stranger the picture becomes. Neutron stars exhibit behaviors that cannot yet be explained, anomalies that hint at physics not yet discovered. Some may harbor exotic matter, hyperons, kaons, or even deconfined quarks, swimming freely in a dense plasma. These possibilities remain speculative, but the data leaves room for wonder on Earth. Particle accelerators, like CERN's Large Hadron Collider, smash protons together at near light speed, probing the building blocks of matter. Yet even at their peak, they cannot recreate the conditions inside a neutron star. The densities are simply too great, the energies too extreme. Neutron stars, therefore, are the ultimate laboratories, natural experiments written into the cosmos. By observing their pulses, their glitches, their emissions, humanity can test theories of matter that no experiment on Earth can confirm. They provide insights into the equation of state, the relationship between pressure and density at nuclear scales. This equation remains one of the great unsolved problems of physics, crucial for uniting quantum mechanics with general relativity. Every observation of a neutron star is a data point in this larger quest. The timing of pulsars, the brightness of X-ray emissions, the gravitational waves of their collisions, all are measurements of matter under impossible conditions. The NICER experiment aboard the ISS has already measured the size of neutron stars to within kilometers, helping constrain their interior structure. LIGO and Virgo continue to monitor the sky for the ripples of merging stars, each event refining our models of nuclear physics. The square-kilometer array, now under construction, promises to multiply our catalog of pulsars by orders of magnitude, opening new vistas of discovery. In probing the dead hearts of stars, humanity peers into a domain where physics falters. These remnants of collapse, these improbable survivors of stellar death, reveal truths that unsettle and inspire. They tell us that matter is not fixed, that the building blocks of reality are malleable under pressure, that gravity can rewrite the rules of existence. Neutron stars should be silent, unreachable, unknowable. Yet through the ingenuity of science, radio telescopes listening to their pulses, X-ray observatories imaging their surfaces, gravitational detectors catching the ripples of their collisions, they speak in whispers of radiation, in the precision of their timing, in the tremors of their glitches, in the cataclysms of their mergers. Each detection is more than a measurement. It is a message carried across the gulfs of space and time. from the edge of physics itself. Neutron stars are no longer phantoms. They are teachers, and in their harsh lessons, humanity confronts not only the limits of science, but the fragility of certainty itself. The deeper humanity peers into the cosmos, the stranger neutron stars become. What began as theoretical curiosities, and then, as faint, regular pulses of radio light, has grown into a menagerie of extremes. Neutron stars do not simply sit as quiet relics of stellar death. They spin, they quake, they merge, and they create elements that give rise to worlds. They are not passive monuments to collapse, but restless, dynamic entities that continue to unsettle every assumption about matter, gravity, and the fate of stars. Some neutron stars rotate at dizzying speeds. Millisecond pulsars, spun up by siphoning matter from a companion star, whirl hundreds of times each second. Their surfaces race at a fraction of light speed. Entire city-sized bodies rotating faster than a hummingbird's wings. The stability of these rotations is baffling. Physics tells us that the centrifugal forces should tear such an object apart. Yet they endure, balanced on the razor edge of collapse and disintegration. The fastest known pulsar, PSRJ 17482-2446 AD, spins at 716 times per second. Its equator hurtles through space at nearly a quarter the speed of light. And yet, it does not break. Instead, it emits radio pulses so precise that scientists have used them as cosmic clocks, testing the limits of Einstein's relativity, and even searching for the faint tug of gravitational waves. Such rapid motion forces reflection. How can matter, crushed beyond recognition, also dance with such grace? These are corpses of stars, yet they move with the vitality of creation itself. Their velocity becomes a paradox, destruction born into motion, decay that sings across the galaxy in rhythms no human hand could replicate. If speed unsettles, magnetism terrifies. Among neutron stars exist the most powerful magnets known to physics, magnetars. Their fields are so strong, 1,000 trillion times that of Earth's, that they distort the quantum vacuum, polarizing the empty space around them. Within a magnetar's field, chemistry itself is rewritten. Atoms stretch into needle shapes, their electrons forced into unnatural alignment. Occasionally, these stars unleash bursts of fury. In 2004, a magnetar named SGR 1806-20 released a flare of gamma radiation so intense it briefly disturbed Earth's ionosphere from 50,000 light-years away. Had it been closer, it would have sterilized our planet. The energy unleashed in 1/10 of a second exceeded the sun's output over 150,000 years. Such power defies comprehension. The magnetic fields of magnetars seem to strain the fabric, reality itself. They suggest that the laws of physics, under ordinary conditions, are but fragile arrangements, ready to collapse into chaos under greater pressure. And they raise a haunting question. If the vacuum itself can be twisted, what does that say about the stability of the universe we inhabit? Perhaps the most spectacular revelations of neutron stars come when they meet their end, not in isolation, but in collision. When two neutron stars spiral together, their dance ends in an explosion so violent that it shakes the very fabric of spacetime. On August 17, 2017, Detectors in Louisiana and Washington recorded a gravitational wave signal that lasted over 100 seconds. It was the fingerprint of two neutron stars colliding 130 million light-years away. Almost instantly, telescopes around the world turned to the same region of the sky. They saw a brilliant flare of light across the spectrum: gamma rays, X-rays, ultraviolet, optical, radio. For the first time, humanity witnessed a single event in multiple messengers, ripples of space-time, and the light of matter itself. The collision, designated GW170817, was more than an astronomical spectacle. It was an act of cosmic alchemy. In the debris of that merger, heavy elements were forged: gold, platinum, uranium. These materials, rare and precious on Earth, were born in the heart of neutron star collisions. Every ring of gold, every circuit of platinum, every relic of heavy metal that humanity has ever held is a gift from such cataclysms. This discovery answered a question that had lingered for decades. Where do the universe's heaviest elements come from? The fusion in ordinary stars could not explain them, nor could supernova alone. It is in the death dance of neutron stars that matter achieves its richest transformations. The Earth itself carries their legacy in its crust, its oceans. Some, under greater mass, cross the critical threshold and collapse into black holes. Others endure, holding their impossible density against gravity's relentless pull. Why do some persist and others vanish into the abyss? This tension defines one of astrophysics' greatest mysteries: the line between neutron star and black hole. The Tolman-Oppenheimer-Volkoff limit, around 2 to 3 solar masses, marks the approximate boundary. Recent observations have revealed neutron stars heavier than previously believed possible, such as JO740 plus 6,620, weighing about 2.14 solar masses. These outliers suggest that the limit may not be as sharp as once thought. What decides the fate of a collapsing core? Is it rotation, magnetic fields, the equation of state of matter itself? The cosmos does not yet reveal its secrets, but each neutron star sits precariously near the edge, a survivor in a realm where survival itself is improbable. As instruments sharpen their gaze, stranger possibilities emerge. Some scientists propose that within neutron stars lies not merely compressed neutrons, but something more exotic. If the pressure is great enough, neutrons may dissolve into their constituent quarks, up, down, and strange. The result could be a strange star, a body of quark matter, unlike anything else in the universe. Such stars would be even denser than neutron stars, their interiors seas of unbound quarks. They may reveal themselves through unusual signals, sharper pulses, unusual cooling rates, or anomalous mass-radius relationships. Yet confirmation remains out of reach. For now, they exist at the edge of speculation, a possibility whispered by theory and hinted at in data. Even more radical is the suggestion that neutron stars may not be stars at all, but windows into entirely new physics. Some theories propose they could harbor stable lumps of strange matter, potentially more stable than ordinary matter itself. If true, the existence of even a single strange star could imply that all matter in the universe is only temporarily stable, that given the right conditions, everything could dissolve into this lower energy state. It is a terrifying thought that neutron stars are not only strange, but contagious. That the universe itself rests upon a fragile foundation of matter, and that its stability is less permanent than it appears. As the mystery deepens, neutron stars force reflection, not just on physics, but on existence. They remind humanity that the universe is not bound by intuition, that what seems impossible can persist, that matter itself can be stretched, twisted, and reborn under conditions that shatter comprehension. A neutron star spinning hundreds of times per second. A magnetar warping the quantum vacuum. Two dead suns colliding to create gold. Each phenomenon is more than an astronomical fact. Each is a parable of endurance, destruction, and transformation. They remind us that creation and annihilation are not opposites but partners, bound in cycles older than galaxies. Why do some neutron stars hold against collapse, while others vanish into black holes? Why does matter sometimes endure and sometimes surrender? The universe offers no final answer, only the haunting reminder that survival itself is a fragile victory. The deeper science probes into neutron stars, the more improbable they become. They spin with the speed of impossibility. They hold magnetism that bends reality. They collide in explosions that seed worlds with gold. They exist in a balance so delicate that a fraction of mass, a breath of energy, could determine whether they live or fall into eternal darkness. They should not exist, yet they do. And in their existence lies a message that reality is stranger than belief, that matter is more flexible than certainty, that even in death, stars may continue to shape the universe. Neutron stars are not only remnants of collapse, they are engines of transformation, keepers of paradox, reminders that the cosmos is not static but alive, restless. For beyond the paradox of their survival lies an even greater frontier, the theories that attempt to explain them, and the possibility that the known laws of physics collide like tectonic plates, grinding against each other in tension that neither can resolve. General relativity, Einstein's grand description of gravity, governs the star's immense pull. Quantum mechanics, the strange language of particles, dictates the behavior of neutrons under crushing pressure. In ordinary circumstances, these two frameworks coexist, their domains separate. But in neutron stars, they are forced into confrontation, and in that confrontation lies one of the greatest mysteries in science. General relativity describes the star as a curve in spacetime, a well so deep that even light bends as it escapes. It predicts the immense gravity, the distortion of time, the warping of nearby orbits. But relativity does not speak of neutrons, of superfluid interiors, or of particles locked into quantum states. It sees only mass and curvature, geometry, and energy. Quantum mechanics, on the other hand, does not acknowledge spacetime as curved. It deals in probabilities, in uncertainty, in exclusion principles that forbid particles from collapsing into identical states. It explains why neutrons resist further compression, how degeneracy, pressure, holds back the abyss. But it does not account for the star's crushing gravity, the warping of time, the gravitational redshift of its light. Here, inside neutron stars, these two pillars of science stand face to face, and both falter. Relativity, says the star, should collapse. Quantum mechanics insists it must resist. Reality itself emerges from their standoff. This conflict is not just academic. It is the same riddle that defines black holes, the early universe, and perhaps even the very nature of reality. Neutron stars are, in essence, laboratories where the tension between the large and the small, the cosmic and the quantum, is inscribed into matter itself. At the center of the mystery lies the equation of state, the mathematical description of how matter behaves at extreme densities. On Earth, equations of state describe gases, liquids, and solids with relative certainty. But inside a neutron star, where densities reach several times that of an atomic nucleus, no experiment can reproduce the conditions. Does matter behave like a degenerate sea of neutrons? Does it transition into exotic phases of quarks and gluons? Does pressure rise sharply with density, or does it soften? Each possibility leads to a different destiny for the star, whether it survives as a neutron star, collapses into a black hole, or becomes something stranger still. NASA's NICER instrument has already measured pulsars with radii around 12 to 13 kilometers, providing constraints on the equation of state. LIGO's detections of neutron star mergers add further clues as the way the stars deform during collision encodes their internal structure. Yet, even with these advances, the true equation of state remains elusive, hidden like a script written inside matter's final fortress. At its most basic, the resistance of neutron stars is explained by degeneracy pressure. According to the Pauli exclusion principle, no two identical fermions, particles like electrons, protons, and neutrons, can occupy the same quantum state. When gravity crushes matter, this exclusion creates pressure. For white dwarfs, electron degeneracy holds the star together. For neutron stars, it is neutron degeneracy. This principle is astonishing. The survival of a star against collapse rests not on tangible forces, but on the invisible bookkeeping of quantum mechanics, the insistence that no two particles can be identical. In the silence of collapsed cores, this law stands as the final defense against annihilation. But does it suffice? The heaviest neutron stars discovered so far weigh over to solar masses. At such densities, even degeneracy pressure may fail, forcing matter into new, exotic states. Exotic matter beyond neutrons. Theorists have long speculated that inside neutron stars, matter may transition into unfamiliar forms. Hyperons. At high densities, neutrons may transform into hyperons, particles containing strange quarks. These hyperons could lower the pressure, making collapse more likely. But their behavior is uncertain. KAON condensates. Some models suggest that mesons like kaons could form a condensate, an exotic soup that alters the star's stability. Quark plasma. Perhaps the most tantalizing possibility is that neutrons themselves dissolve, releasing their constituent quarks into a free-flowing plasma. This quark matter would be denser and more uniform than neutron matter, resembling the state of the universe microseconds after the Big Bang. If such transformations occur, they would mean that neutron stars are not truly neutron stars at all, but gateways to new phases of matter. They would be cosmic laboratories where the early universe still lingers. Stars, objects composed not of neutrons, but of strange quark matter. According to this idea, strange quark matter may be more stable than ordinary matter. If even a small drop of it exists inside a neutron star, it could spread, converting the entire star into a strange star. Such objects would be even denser and more compact, their surfaces smoother, their pulses sharper. They may already exist, hidden among pulsars we have mistaken for ordinary neutron stars. But their detection would mean something profound, that all matter in the universe may be metastable, and that the ordinary protons and neutrons we depend on are not the most stable form of matter after all. This speculation is not mere fantasy. Observations of unusually small neutron stars, or stars with unexpected cooling rates, hint at such possibilities. Yet the evidence remains incomplete, awaiting more precise instruments, more collisions, more whispers from the dead hearts of stars. In the attempt to understand neutron stars, physicists find themselves wielding two incomplete languages. At the macro scale, Einstein's relativity governs the star's gravitational collapse, its space-time curvature, the warping of nearby orbits. At the microscale, the physics of Enrico Fermi and others governs neutrons, quarks, and nuclear forces. But the two frameworks do not merge. Each insists on its own truth. Relativity denies the quantum fluctuations inside matter. Quantum mechanics ignores the geometry of spacetime. In neutron stars, both are required, yet neither suffices. This gap is why neutron stars are more than astronomical curiosities. They are testbeds for unification, cosmic reminders that our theories remain incomplete. The true description of their interiors may require a new theory altogether, a quantum theory of gravity, a long-sought unification of the large and the small. Stephen Hawking often reflected on compact objects, neutron stars, black holes, and singularities. He saw in them the places where physics breaks down, where assumptions collapse, where certainty falters. Neutron stars, he argued, are not just dead remnants, but keys to deeper laws. They occupy the space just before the point of no return. The last outpost before collapse becomes absolute. In them, the universe whispers the secrets it hides inside. Black holes but still allows us to glimpse. If black holes are locked vaults of information, neutron stars are the open gateways, laboratories of extreme physics that still speak to the outside world. Some theorists stretch further, asking whether neutron stars themselves may be shaped by the constants of the universe. If the strong nuclear force were slightly weaker, neutrons would not bind, and neutron stars could not exist. If gravity were slightly stronger, they would collapse into black holes. This fine balance suggests a deeper question. Do neutron stars exist only because the laws of our universe allow them? In other universes, with other constants, they may be impossible. In this sense, neutron stars become not just astronomical objects, but reflections of the universe's very parameters. They are monuments to the tuning of physical laws, perhaps, even hints of a multiverse where such tuning plays out differently. The tension between known science and speculation is stark. On one side lies observation, pulses timed with precision, X-rays, measured gravitational waves recorded. On the other lies theory, quark matter, strange stars, new phases of existence. Neutron stars straddle both worlds. They are real and observable, yet they invite speculation that stretches science to its limits. They are reminders that progress does not come only from what we know, but from daring to imagine what might be. Are neutron stars windows into new physics? Stars, or the unification of relativity and quantum mechanics? They force us to confront the limits of knowledge. At the edge of physics, neutron stars stand like sentinels. They are both proof and question, both answer and paradox. They embody the clash between relativity and quantum mechanics, the mysteries of matter's ultimate state, the possibility of worlds stranger than ours. Each pulse from a neutron star is more than a rhythm. It is a message that reality is not finished, that physics is not complete, that the universe still holds chapters unwritten. In their interiors may lie the key to unification, the secret of matter's deepest form, the bridge between the quantum and the cosmic. They remind humanity that every certainty may crumble, every law may falter, every truth may hide deeper truths beneath. Neutron stars are not just remnants of collapse. They are thresholds. They are experiments set by the universe itself. And at their edge lies not only physics, but the possibility of entirely new realities waiting to be unveiled. The mysteries of neutron stars do not yield easily. They are hidden in shadows, wrapped in silence, and cloaked by distances too vast for human intuition to grasp. They emit no warmth that human skin could feel, no light that human eyes could see unaided. To study them, humanity has had to create new senses, instruments that extend beyond flesh and bone, machines that allow Earth to listen, to feel, and to glimpse what would otherwise remain unseen. Each tool humanity has built is more than metal and circuitry. It is a question cast into the dark. And with each detection, the cosmos replies, slowly, carefully, revealing fragments of truth from the hearts of stars that should no longer exist. Aboard the International Space Station, orbiting above Earth's haze, sits a small but extraordinary instrument. The Neutron Star Interior Composition Explorer NICER peers across the void with purpose unlike any other. Its design is deceptively modest, an array of X-ray detectors focused not on galaxies or nebulae, but on the compact remnants of collapsed suns. NICER's goal is audacious: to weigh and measure neutron stars, to map their size and structure, to constrain the elusive equation of state. By timing the arrival of X-rays emitted from pulsars, NICER can infer the curvature of space-time around the star, the warping of its light by gravity, and the bending of its beams as they sweep across the universe. Already, NICER has yielded revelations. It measured the pulsar J0030 plus 0451, finding it to be about 1.4 times the mass of the Sun, yet only 26 kilometers wide. Its results narrowed the possibilities of neutron star interiors, ruling out equations of state that predicted stars either too small or too large. In each pulse, NICER hears the heartbeat of matter crushed to nuclear densities, and through mathematics and inference, it translates that rhythm into knowledge. While NICER measures pulses, another set of instruments listens for something deeper: the rippling of space-time itself. The Laser Interferometer Gravitational Wave Observatory, LIGO, together with Virgo in Italy and Kagra in Japan, has transformed astronomy. These detectors do not look outward. They measure distortions in the very fabric of reality as gravitational waves pass through Earth. In 2017, they recorded the collision of two neutron stars, an event known as GW170817. The signal lasted over 100 seconds, a slow crescendo as the stars spiraled inward. When they merged, a flash of light followed, captured by telescopes worldwide. This was more than an astronomical triumph. It was a new way of knowing. For the first time, the cosmos was observed not only in light, but in gravity itself. Gravitational wave astronomy is still in its infancy. Its detectors are sensitive to ripples smaller than the width of a proton. Yet even this delicacy only glimpses the most violent events. Future upgrades and the proposed space-based LISA mission promise even greater clarity. Each detection is more than a signal. Under the most extreme conditions imaginable, to truly understand neutron stars, no single wavelength suffices. Their mysteries unfold across the spectrum. From radio to gamma rays, NASA's Chandra X-ray Observatory has been a sentinel in orbit since 1999, capturing the hot glow of neutron stars as they cool. It has revealed pulsar wind, nebulae, shock waves of energy carved into surrounding space, and X-ray flares from magnetars that momentarily rival the brightness of entire galaxies. The Hubble Space Telescope, though built for optical light, has contributed by observing pulsars in visible bands, confirming their faint flickers across the void. And now, the James Webb Space Telescope extends humanity's reach into infrared, in dust, or the echoes of mergers hidden from other eyes. Together, these instruments weave a tapestry of sight. Each frequency tells a different story. Radio waves reveal pulses, X-rays expose surfaces, optical light shows faint remnants, infrared unveils hidden dust, gamma rays catch violent flares. To understand neutron stars, humanity must see not with one eye, but with many, stitching together their fragmented signals into a portrait of the impossible. Yet even photons and gravitational waves are not enough to truly catch the birth of a neutron star. Scientists look for particles even stranger, neutrinos. These ghostly messengers stream from supernova, carrying direct information from a collapsing core. In 1987, detectors recorded a handful of neutrinos from a supernova in the Large Magellanic Cloud SN 1987A. It was a moment of astonishment, a whisper from a dying star reaching Earth through particles that almost never interact with matter. Those neutrinos were evidence of a core collapsing into a neutron star, proof of nuclear physics unfolding in real time. Since then, neutrino detectors have grown larger and more sensitive. Instruments buried deep in ice, like IceCube in Antarctica, or submerged in water, like Super Kamiokande in Japan, now wait for the next nearby supernova. When it comes, thousands of neutrinos will be recorded, offering the most direct look into the moment of stellar death. These ghostly signals are not just data, they are glimpses of transformation carried by particles that pass through planets and stars as though they were shadows. They are the closest humanity will come to touching the moment when a star collapses into a neutron star. Even with telescopes and detectors, much of the neutron star remains hidden. Its core, sealed beneath kilometers of nuclear matter, cannot be observed directly. To bridge this gap, scientists turn to simulations, numerical models run on supercomputers, translating equations into approximations of reality. These simulations attempt to recreate the physics of collapse, rotation, magnetism, and matter at densities beyond experiment. They explore how neutrons arrange themselves, how quarks might flow, how superfluids might ripple inside the star. Yet simulations to face limits. The true equation of state remains uncertain. Nuclear forces at such densities are not fully known. Computing power cannot capture every quantum fluctuation. Each model is an approximation, a sketch drawn in the margins of ignorance, and yet they are indispensable. They guide observations, predict signals, and frame questions. Without them, the raw data from telescopes would remain mute. With them, data and theory converse, each correcting and refining the other, step by step, toward truth. The tools of today are powerful, but the cosmos demands more. The next generation of instruments promises deeper vision. The Square Kilometre Array, SKA, now under construction across Australia and South Africa, will be the largest radio telescope ever built. With its vast collecting area, it will discover thousands of new pulsars, mapping the galaxy with unprecedented precision. Its timing will allow tests of relativity with exquisite detail, perhaps even revealing low-frequency gravitational waves from supermassive black holes. The Athena Observatory, planned by the European Space Agency, will provide sharper X-ray vision than ever before. It will probe the surfaces of neutron stars, measure their magnetic fields, and constrain their interior structure. Other projects, like the Einstein telescope in Europe or the Cosmic Explorer in the United States, aim to extend gravitational wave astronomy into new frequency ranges. Listening to the universe with greater sensitivity and over greater distances together. These future instruments are not just technological advances, they are windows into tomorrow, promises that the secrets of neutron stars will not remain hidden forever. Science does not conquer mysteries in sudden triumph. It unveils them slowly, carefully, through patience and persistence. Neutron stars remind humanity of this truth. For decades, they were only theories. Then pulses revealed their presence. Then X-rays showed their glow. Then gravitational waves captured their collisions. Piece by piece, the cosmos allows its secrets to be known, but the unveiling is never complete. Each new instrument answers questions and raises others. Each discovery deepens the paradox. The closer science comes, the more elusive the truth appears. Neutron stars resist finality, as though guarding the edge of physics with riddles no single tool can solve. And yet, the pursuit continues. Humanity builds new senses, extends new eyes, crafts new ears for the universe. With each step, the darkness recedes a little further. With each detection, the cosmos grows more familiar and more mysterious at once. The tools of today are not the end, but the beginning. They are questions made solid, curiosity shaped into machines, patience given form in orbiting observatories, and buried detectors. They extend human perception into realms where no flesh could survive, where no eye could see, where no hand could touch. Through them, neutron stars cease to be silent phantoms. They become participants in a dialogue between cosmos and consciousness, between collapse and comprehension. Each pulse measured by Neisser, each ripple caught by LIGO, each neutrino recorded in the ice, is a syllable in that dialogue, a fragment of a story still unfolding. The future promises clearer voices, sharper signals, deeper truths, but the essence will remain the same. Science as a slow unveiling of the unseeable. Patience rewarded by glimpses of the impossible. Instruments as bridges across the abyss. Neutron stars are not yet fully known. But with every tool humanity builds, the window grows wider. And through that widening window, the universe leans closer, whispering its secrets, daring us to listen. The story of neutron stars is not only written in the language of equations and instruments. It is also a story of symbolism, of meaning, of how fragile beings on a small planet contemplate objects so dense, so alien, that they seem to belong more to myth than to science. They are the remnants of destruction, the ashes of giants, yet they endure as condensed lanterns in the dark, and in their endurance they hold a mirror to the human condition itself. Every neutron star is born in violence. A supernova tears a massive star apart, scattering its outer layers across the galaxy, lighting the sky with brilliance that can outshine an entire galaxy for a brief, dazzling moment. It is the ultimate act of destruction, yet from this death emerges something that does not die. The neutron star that remains is not the living sun it once was, nor is it entirely gone. It is a survivor, transformed beyond recognition, compressed to the edge of physics, yet still present, still radiating, still spinning its pulses into the cosmos. Here lies the first meaning of neutron stars, that death is not always annihilation, but transformation. They are monuments to endurance, testaments that even when matter collapses and identity dissolves, something persists. The balance between ending and continuation, between annihilation and rebirth, is carved into their very being. For humanity, fragile and finite, the sight of such persistence is both humbling and inspiring. These stars remind us that endings may hold within them the seeds of continuity, that collapse does not always mean disappearance, and that even in death there can be a kind of endurance. Neutron stars embody impermanence. They are proof that even the greatest suns, shining for millions of years, cannot escape collapse. No star is eternal. No light endures forever. The cosmos itself is a stage of constant birth and death, where galaxies collide, black holes devour, and stars are born and extinguished in endless rhythm. And yet, neutron stars also embody endurance. They survive at the edge of collapse, resisting gravity's hunger with quantum laws invisible to the human eye. They endure pressures that would obliterate any ordinary substance. They hold together against every intuition, refusing to surrender. To the void, in this duality, lies a lesson. Impermanence and endurance are not opposites, but partners. Just as a neutron star arises from destruction, so too endurance is forged through impermanence. Humanity, with its fleeting lives and fragile bodies, may see in them a symbol of our own struggles to persist against time, to carry memory beyond the grave, to endure in the face of inevitability. Supernova are catastrophic, yet they are also creative. In their fury, they forge the heavy elements that make planets, oceans, and life itself. In their collapse, they leave behind neutron stars or black holes, compact objects that reshape their surroundings with gravity, magnetism, and light. Neutron stars, in particular, remind us that destruction and creation are intertwined. Their mergers create gold, platinum, and uranium, the very elements that shape human culture and civilization. Their pulses serve as cosmic clocks, guiding spacecraft and testing the structure of spacetime. Their existence pushes science toward unification, forcing humanity to seek new theories and deeper truths. Thus, even as they are monuments to destruction, neutron stars are also fountains of creation. They embody the paradox that the universe itself is woven from, that every act of ending births a beginning, that collapse and formation are two sides of the same cosmic rhythm. Perhaps the most haunting reflection neutron stars offer is on the fragility of physics itself. On Earth, the laws of matter feel immutable. Atoms seem stable. Matter feels solid. Gravity is weak. Time flows steadily. The world seems permanent. Yet inside neutron stars, these certainties dissolve. Neutrons, ordinarily stable only within atomic nuclei, become the building blocks of entire stars. Quantum exclusion, a law that governs electrons in atoms, becomes the force that holds back the collapse of suns. Gravity, usually imperceptible in daily life, becomes overwhelming, bending light and stretching time. The laws of physics reveal themselves to be conditional, contingent upon scale and circumstance. What feels stable is only stable here, in this narrow band of existence we call home. Beyond it, in the dense hearts of collapsed suns, stability frays and the laws we rely upon begin to tremble. This fragility should not terrify but awaken it. Reveals that physics is not a rigid edifice, but a living structure, one that bends, transforms, and adapts across the vastness of the cosmos. Neutron stars are the cracks in that structure, the places where light slips through, reminding humanity that knowledge is never final and that certainty is always provisional. Against the scale of neutron stars, humanity seems impossibly small. A teaspoon of neutron matter outweighs mountains. A pulsar's rotation surpasses the precision of atomic clocks. A magnetar's field could erase every trace of chemistry on Earth compared to such forces. A human life seems like a flicker, fragile and transient, and yet there is meaning in the act of contemplation itself. Fragile beings, made of dust and breath, can look up and not only see these objects, but measure them, time them, simulate them, and imagine their interiors. Humanity, though vulnerable, extends itself through knowledge, reaching across gulfs of space and time to touch the impossible. This act of contemplation is not trivial. It is a form of endurance. Though human lives pass quickly, though civilizations rise and fall, the act of knowing continues, preserved in books, instruments, and memory. In studying neutron stars, humanity inscribes itself into the cosmos, leaving a trace as enduring as the pulses of collapsed suns in their silence. Neutron stars are keepers of memory. They remember the suns they once were. They carry the imprint of supernova long since faded. They store within their core the conditions of the early universe, the pressures and densities that defined creation itself. To observe a neutron star is to glimpse not only an object, but a record. Each pulse is a timestamp, each merger a signature, each anomaly a reminder of histories written in collapse and endurance. They are cosmic archivists, lanterns of physics burning in the dark, preserving the memory of what came before, and perhaps, in reflecting upon them, humanity too becomes a part of that memory. For as long as neutron stars endure, they carry their lessons silently into the future. And as long as humanity listens, measures, and imagines, those lessons echo not only in science, but in meaning. Neutron stars are paradoxes made flesh in the cosmos. They are dead stars that refuse to vanish, symbols of impermanence and endurance, monuments to the fragile and the eternal. They embody destruction and creation at once, revealing the fragility of physics, the tenuousness of certainty, and the vastness of mystery. To look upon them is to confront the limits of understanding, but also to find inspiration. For if the universe can compress suns into objects smaller than cities, if it can bend the laws of matter into unfamiliar forms, then it can also bend human imagination into new shapes. In the end, neutron stars are not only astrophysical objects, they are metaphors for existence itself. They are reminders that collapse does not always mean disappearance, that endings can hold endurance, that fragility and strength are woven together in the fabric of reality. They are silent keepers of cosmic memory, lanterns burning in the night, illuminating the dark with lessons written in matter, in gravity, in collapse. They endure not for themselves, but for the cosmos and for those fragile beings who gaze upward, asking questions and daring to listen.